Hello there, and welcome to Simple Science for Sleep. Right now, while you're settling in for sleep, millions of trees are doing the same thing. They're shutting down for winter, slowing their pulse, entering something that looks a lot like sleep. But here's what scientists are discovering. Trees might actually be dreaming, not the way you dream, with stories and images, but something stranger, something we're only beginning to understand. If this kind of gentle science wonder brings you peace, hit that like button and subscribe so you don't miss more calming stories tomorrow. And drop a comment telling me where you're watching from and what time it is there. It's beautiful knowing we're all connected under the same sky, all sharing this moment with the sleeping forests around the world. Tonight, we're going to drift into the secret winter life of trees, the hidden world beneath the bark, the slow conversations happening in darkness. And by the end, you might never look at a sleeping forest the same way again. So, get comfortable. Pull your blankets a little closer. Let your breathing slow down naturally. We're going somewhere peaceful tonight, somewhere that will change how you see the world outside your window. Picture a forest right now, any forest. Maybe one you've walked through, or one you've only seen in photographs. The trees stand silent, their branches bare against the winter sky. Snow might cover the ground, or maybe just frost sparkles on fallen leaves. Everything looks still, dead even. But that's not what's happening at all. Those trees aren't dead. They're not even really asleep in the way you might think. They're doing something far more interesting. Scientists have spent decades studying what happens to trees in winter, and what they've found is remarkable. Trees don't just shut down randomly when the cold arrives. They prepare, they make decisions, they actively transform themselves into winter survivors. And the process starts long before the first frost touches the ground. It begins in late summer, when the days start getting shorter. The tree notices. It's measuring the sunlight, counting the hours of darkness, reading the world like you might read a calendar. Inside each cell of the tree, changes begin. Chemical signals start flowing through the wood. Hormones rise and fall like tides. The tree is having a conversation with itself, and the message is clear. Winter is coming. Time to get ready. Time to transform. And this transformation is so complete, so total, that by the time winter truly arrives, the tree has become a different version of itself. A winter version, a sleeping version. But sleep for a tree is nothing like the sleep you experience every night. It's deeper, stranger, more mysterious, and scientists are only now beginning to understand what's really happening in those silent months. What the tree is actually doing while it stands there, seemingly frozen in time. As autumn arrives, trees begin the most remarkable transformation. They don't just lose their leaves and wait. They actively prepare for a kind of sleep that will last for months. And this preparation is as complex as anything you might do to get ready for a long journey. The tree is packing, storing supplies, closing doors, locking windows, making itself safe for the long dark ahead. It starts with the leaves. You've seen this happen every fall. The green fades. Brilliant reds and yellows appear. Then the leaves drop, one by one, until the branches stand bare. But this isn't the tree dying, it's the tree being smart. Those leaves are expensive to maintain. They need water constantly. They can freeze and burst in the cold. So the tree cuts them loose. But before it does, something incredible happens. The tree pulls everything useful out of those leaves, all the valuable nutrients, the nitrogen, the phosphorus, every bit of chlorophyll that made the leaves green. The tree sucks it all back into the branches, into the trunk, down into the roots. It's recycling, saving everything it can before winter arrives. That's why leaves change color. You're watching the green chlorophyll disappear as the tree reclaims it. The reds and yellows were there all along, hidden beneath the green. Now they shine through. Once the nutrients are safely stored, the tree does something even more remarkable. It builds a wall. Right at the base of each leaf stem, the tree grows a layer of cells that blocks the connection. It's called an abscission layer. This wall cuts off water and nutrients to the leaf. The leaf dies, the connection weakens, and then, with the next strong wind or the next cold night, the leaf falls. The tree has let go, not carelessly, but deliberately, carefully, with purpose. But this is just the beginning of the great shutdown. Inside the tree, deeper changes are happening. Water is being moved around. The tree is pulling moisture out of its outer cells and concentrating it deeper inside, where it's safer from freezing. It's like draining the pipes in a house before winter, so they won't burst. The tree knows the cold is coming. It's preparing every cell for what's ahead. Sugars that the tree made all summer through photosynthesis are being stored, packed away in root cells, tucked into the wood of the trunk. These sugars are the tree's fuel for winter, its savings account. The tree will live off these stored sugars for months, burning them so slowly you couldn't measure the heat. But that fuel is essential. Without it, the tree would die in its sleep. The tree is also changing the chemistry of its cells. It's pumping in special proteins, adding compounds that work like antifreeze, adjusting the salt concentration in its sap. All of these changes have one purpose: to let the tree survive temperatures that would normally kill it. The tree is transforming itself into a winter survivor, and this transformation takes weeks. It's not instant, it's gradual, careful. By the time the first hard freeze arrives, the tree is ready. It has become something new, something dormant, something that can survive until spring. The great shutdown is complete, and now the real mystery begins. Deep in the tree's tissues, a chemical conversation begins. This isn't something you can see from the outside, no visible signs. But inside, at the level of cells and molecules, the tree is talking to itself, sending messages, giving orders, and the language it uses is made of hormones, chemical signals that flow through the wood like whispered instructions in the dark. The most important of these chemicals is called abscisic acid. Scientists gave it this name because they first discovered it when studying how leaves fall off, that abscission process we talked about. But this hormone does so much more. It's the tree's master switch for survival. When abscisic acid levels rise, everything changes. The tree begins to shut down, to protect itself, to enter dormancy. Think of abscisic acid as the tree's way of saying, danger is coming, time to be careful. This same chemical helps the tree survive drought in summer. When water gets scarce, abscisic acid rises. It tells the tiny pores in the leaves to close tight. It stops the tree from losing precious moisture. The tree goes into conservation mode. And now, as winter approaches, the same hormone rises again. But this time, it's not just about saving water, it's about surviving the cold. As abscisic acid floods through the tree, other hormones respond. Auxins, which normally promote growth, start to decrease. These are the chemicals that tell cells to divide, to expand, to build new tissue. But in winter, growth is dangerous. New cells are tender, vulnerable. They would freeze and die. So the auxins fade away. The tree stops growing. All that energy that went into making new leaves and branches in spring and summer now gets redirected, stored, saved. Another hormone called cytokinin also drops. This chemical usually keeps cells active and awake. It's like the tree's caffeine. But as winter comes, cytokinin levels fall. The cells become drowsy. Their metabolism slows. They're preparing for that long sleep. And yet another hormone, ethylene, starts to rise. This one helps with the final stages of shutting down. It assists in breaking down cell walls in those abscission layers. It helps the tree let go of the last leaves. It smooths the transition into dormancy. What's remarkable is how coordinated all of this is. These hormones don't work alone. They interact. They balance each other. They create a chemical symphony that guides the tree through its transformation. Scientists can measure these hormone levels. They can track how they change day by day as autumn progresses. And what they see is beautiful. It's precise. It's elegant. The tree knows exactly what it's doing. This chemical conversation happens in every tree. In the oak in your backyard. In the maple lining your street. In the massive sequoias of California and the tiny birches of the Arctic. Each species has its own timing, its own exact recipe of hormones. But they're all speaking the same basic language. The language of survival. The language of sleep. And this language is ancient. Trees have been perfecting it for hundreds of millions of years. Every winter is a test. Every spring is proof that they got the chemistry right, that they listened to their own chemical wisdom and survived another round of cold and darkness. Trees have a pulse. This sounds impossible, but it's true. Scientists can measure it. They attach sensitive instruments to the trunk, and they can detect movement. Water moving up from the roots to the branches, not in a steady stream, but in waves. Pulses, like a heartbeat. During the growing season, this pulse is strong. You can almost think of it as the tree breathing, drawing water up from deep in the soil, pulling it through the wood, sending it out to every leaf. This flow is constant, rhythmic, alive. But as winter approaches, something changes. The heartbeat slows, not all at once. Gradually, day by day, the pulses become weaker, slower, further apart. The tree is reducing its circulation. It's like when you settle into bed at night and your own heart rate drops. Your body knows it's time to rest. Your pulse becomes gentler, quieter. The tree is doing the same thing, just on a much longer timescale. Why does this happen? Because moving water takes energy. The The tree has to work to pull moisture up from the roots. It has to overcome gravity. It has to create pressure differences. All of this requires fuel, requires metabolism, requires the tree to be active. But in winter, there's no point. The leaves are gone. There's nothing up there that needs water. And besides, moving water in freezing temperatures is dangerous. Water expands when it freezes. If the tree kept pumping water up into its branches during a hard freeze, ice crystals could form. Those crystals could tear apart cells, destroy tissue, kill the tree from the inside. So the tree slows its pulse down to almost nothing. Almost, but not quite. There's still a tiny bit of movement, just enough to keep the deepest cells alive, just enough to maintain that thin thread of life through the winter months. Scientists have measured this. They've found that even in the coldest part of winter, when the tree looks completely dormant, there's still a whisper of flow, still a barely detectable pulse. The tree isn't dead. It's just resting very, very deeply. This slowed pulse is one of the most beautiful adaptations trees have developed. It's a perfect balance. Too much circulation and the tree wastes energy and risks ice damage. Too little and cells start dying from lack of moisture. But the tree has learned, over millions of years, exactly where that balance point is. Exactly how slow the pulse can go while still maintaining life. It's like the tree is hovering right on the edge between life and death. Not quite either one, suspended in between. When you're falling asleep tonight, notice your own heartbeat. Feel how it slows as you relax, how your breathing deepens and becomes more regular, how your body knows exactly how to transition from waking to sleeping. The tree is doing something similar. Its pulse is slowing into dormancy. Its circulation is becoming a whisper. And just like you trust your body to keep your heart beating while you sleep, the tree trusts its ancient wisdom to maintain that tiny pulse through the long winter. Just enough to survive. Just enough to dream. Just enough to wake again when spring returns. But here's where it gets interesting. Even as the tree above ground goes quiet, something else stays awake. Below the soil, hidden from view, the roots remain active. Not fully active like they are in summer, but not sleeping either. The roots are doing something remarkable. They're staying connected, because trees aren't alone down there. They're part of a network, an underground web that links them together in ways we're only beginning to understand. This network is made of fungi, tiny threads of fungal tissue that wrap around tree roots and spread through the soil. Scientists call these mycorrhizal fungi. The name means root fungus. And these fungi form partnerships with trees. The fungus connects to the tree's roots. It helps the tree absorb water and nutrients from the soil. In return, the tree shares some of its sugars with the fungus. It's a fair trade. Both partners benefit. Both need each other to thrive. But what makes this really amazing is how far these fungal networks spread. A single fungus can connect to multiple trees, and those trees can be connected to other trees through other fungi. The result is a web, an underground internet, some scientists call it. Trees linked to trees through soil and fungus across entire forests. And through this network, they can communicate. They can share resources. They can help each other survive. Even in winter, this network keeps working. The fungal threads don't freeze like the tree's water-filled cells might. They're smaller, more flexible, better protected in the soil. So, while the tree above ground slows down, the roots and their fungal partners maintain their connection. Messages still pass through, chemical signals, warnings about threats, shares of stored nutrients. It's like the forest has a backup communication system that works even when the main system shuts down for winter. Scientists have discovered that mother trees, the big old trees in a forest, use this network to support their offspring. Even in winter, a large tree can send carbon to smaller trees nearby. Carbon that came from sugars stored last summer. The mother tree is literally feeding her children through the dark months, keeping them alive when they might not have enough stored energy of their own. It's cooperation, it's community. It's something that seems almost like care. And it's not just parent to child. Trees will help neighbors of completely different species. An oak might share resources with a maple. A pine might support a birch. Through the fungal network, the forest acts as one organism, one community. When one tree has extra resources, it shares. When another tree is struggling, it receives help. This keeps happening even when the trees themselves are dormant, even when they're dreaming their winter dreams. So the tree standing silent in the snow isn't truly alone. Its roots are holding hands with other roots underground. The fungal network connects them all. And this connection never fully sleeps. It's always there, always working, always linking tree to tree across the winter landscape. The forest sleeps, but the forest also watches over itself. Through the soil, through the fungi, through connections we can't see, but that make all the difference between survival and death in the cold months ahead. Trees remember. They have to. Each winter, they need to know when to wake up in spring. Too early, and a late frost kills them. The tender new leaves freeze. The flowers die. All that stored energy gets wasted. Too late, and they miss their chance to grow. Other trees grab the sunlight first. The growing season gets shorter. The tree falls behind. So, timing matters. Timing is everything. And to get the timing right, the tree needs to remember. But trees don't have brains. They don't have neurons or memories stored in cells like yours. So how do they remember? How do they keep track of the seasons? Scientists have spent years puzzling over this, and what they've found is fascinating. Trees use chemistry to remember. They use accumulated changes in their tissues. They count. Here's how it works. The tree measures cold, not just whether it's cold, but how long it's been cold. Every day below a certain temperature, the tree registers it. Like making a mark on a calendar, the tree is counting cold days. This process is called chilling, and the tree needs a certain amount of chilling before it will wake up in spring. It's like the tree is making sure, yes, winter really happened. Yes, enough time has passed. Yes, it's safe to grow again. Different trees need different amounts of chilling. An apple tree might need 800 hours below a certain temperature. A peach tree might need less. Trees that evolved in colder climates need more chilling. Trees from warmer areas need less. But they all have their number, their threshold, and they're all counting, all winter long, in the dark. The tree is also measuring something else. Daylight. Even without leaves, the tree can sense light. It has proteins in its bark and buds that respond to different wavelengths of light. These proteins can tell the difference between the short days of winter and the longer days of spring. They're like tiny light sensors scattered throughout the tree, and they're always on, always measuring, always keeping track. So, the tree is running 2 clocks at once. A cold clock and a light clock, and both need to reach the right numbers before the tree will wake. This is how the tree avoids getting fooled by a warm spell in January. Sure, it might be 60 degrees outside, but the light clock says it's still winter. The days are still short, and maybe the cold clock hasn't reached its threshold yet. Not enough chilling hours have passed, so the tree stays asleep. It waits. It remembers that spring is more than just warm weather. Spring is a specific combination of temperature and light, and the tree won't be tricked. This memory system is incredibly sophisticated. It's the result of millions of years of evolution. Trees that woke up too early died in late frosts. Trees that woke up too late got outcompeted. Only the trees with good timing survived. Only the ones who could count cold days and measure sunlight made it. And now, every tree carries this ancient memory system in its cells. This ability to track time without a brain, to remember patterns without conscious thought, to know with absolute certainty when winter has truly ended and spring has truly begun. So, what does a tree dream about? Maybe not dreams the way we think of them. No stories playing out, no images or sounds. But the tree is processing. Its cells are reorganizing. Things are happening in that winter darkness. Things that look a lot like what happens in your brain when you dream. When you sleep, your brain doesn't just shut off. It's incredibly active. It's sorting through everything that happened during the day, deciding what to keep and what to let go, strengthening important connections between neurons, pruning away connections that don't matter, consolidating memories, processing emotions. Your brain is basically doing maintenance, getting ready for tomorrow. And in a strange way, the tree is doing something similar. Inside the dormant tree, cells are being reorganized. Proteins are being broken down and rebuilt. Cell structures are being repaired. Damage from last summer's growth is being fixed. The tree is literally rebuilding itself at a molecular level, taking itself apart and putting itself back together better, stronger, more prepared for the next growing season. This happens so slowly you could never see it. But it's constant. All winter long, the tree is working on itself. There's also something else happening. The tree is pruning, not branches, but connections at the cellular level. Some cells that aren't needed anymore get shut down. Resources get redirected. The tree is making itself more efficient, getting rid of what doesn't work, keeping what does. This is exactly what your brain does when you dream. It's pruning neural connections, keeping the important ones, letting the weak ones fade away. The tree is doing the same kind of maintenance, just in a different form. And then there's preparation. Deep in the buds, cells are organizing themselves. They're getting ready to become leaves, to become flowers. The instructions are already there, written in the tree's DNA. But those instructions need to be activated, prepared, made ready. The tree is rehearsing spring while winter still holds on. It's like practicing a performance before the curtain rises. Making sure everything is in place. Making sure that when the signal comes, the tree can burst into life quickly. Scientists have found that this winter processing is essential. Trees that don't get a proper dormancy period don't grow well. They're confused, disorganized. They've missed their chance to sort themselves out. It's like trying to function without sleep. You can do it for a while, but you're not at your best. You're foggy, inefficient. The tree is the same. It needs this winter dream time to process, to prepare, to get ready for the intense work of spring and summer. So, maybe the tree's dreams aren't about images or stories. Maybe they're about chemistry and structure, about cells reorganizing in darkness, about proteins folding and unfolding, about DNA getting ready to express new genes. But it's still a kind of dreaming, a kind of processing. The tree is sorting through last season and preparing for the next. It's learning from what worked and what didn't. It's getting ready to grow again. And all of this happens in the silence, in the stillness, in the deep winter sleep that looks like nothing but is actually everything. Winter sleep has levels. Some trees sleep deeper than others. An oak in freezing Minnesota enters a profound dormancy. Its metabolism drops to almost nothing. Its cells become like glass, frozen in time, waiting. This tree might experience temperatures of 30 or 40 degrees below zero. It has to shut down completely to survive that kind of cold. There's no other option. Sleep deep or die. But a palm tree in California barely slows down at all. The temperature there might drop to 50 degrees on a cold night. That's not true winter. That's just a cool evening. So, the palm keeps some of its processes running. It keeps growing, just slower. Its version of winter sleep is more like a light nap, a brief rest, not the deep hibernation of the northern oak. And then there are trees in between. A maple in Virginia, a birch in Oregon. These trees experience moderate winters. They sleep, but not as deeply as their northern cousins. They shut down some systems, but keep others ready. They're listening, paying attention, ready to respond if conditions change. Their dormancy is flexible, adjustable. They can go deeper if needed, or wake up a bit if temperatures rise. But all of them, from the deep sleeping oak to the barely resting palm, are doing the same basic thing. They're waiting for the right signals, the right combination of temperature and light and time. Each species has its own requirements, its own code that needs to be entered before it will wake. And the tree is constantly checking. Is it time yet? Have the conditions been met? Should I start preparing to grow? This checking happens even in the deepest sleep. The tree never completely disconnects from its environment. It can't afford to. It needs to know what's happening outside. Is it getting warmer? Are the days getting longer? Has enough time passed? The tree is processing this information constantly, running it through those internal clocks we talked about, those memory systems that count cold hours and measure light. Scientists call this state endodormancy, when the tree is holding itself asleep and ecodormancy when outside conditions are keeping it asleep. The difference matters. A tree in endodormancy won't wake up even if you bring it into a warm greenhouse. It's locked in sleep from the inside. Its internal clocks haven't reached their thresholds yet. But a tree in ecodormancy is just waiting for the weather to improve. Bring it inside, give it warmth and light, and it will wake up. It's ready. It was just waiting for permission from the environment. Most trees move from endodormancy to ecodormancy sometime in midwinter. The internal requirements get satisfied. The chilling hours are met. The light sensors have measured enough darkness. Now the tree is just waiting for spring temperatures, for that final signal that says, now, go, grow. And this is a vulnerable time, because if the weather warms up too early, the tree might wake, and then if cold returns, disaster strikes. The tree has come out of protection mode. It's exposed, tender, and that's when late frosts do their damage. That's when trees die, not from winter itself, but from the betrayal of false spring. Inside a sleeping tree, water performs an impossible trick. It doesn't freeze solid, even when the temperature drops below zero. This should be impossible. Water freezes at 32 degrees Fahrenheit. That's a basic fact. But the water inside a tree can stay liquid at 20 degrees. At 10 degrees, sometimes even at 0. The tree has learned to change the water itself, to transform it into something that doesn't play by the normal rules. The tree does this by adding things to the water. Sugars, mostly. Those same sugars it stored away from summer photosynthesis. But now they have a second purpose. When sugar dissolves in water, it lowers the freezing point. It's the same reason we put salt on icy roads. The salt-water mixture freezes at a lower temperature than pure water. The tree is doing the same thing, but with sugar instead of salt. And it's doing it inside every cell, creating a sweet syrup that can stay liquid even as temperatures plunge. But that's not the only trick. The tree also produces special proteins. Scientists call them antifreeze proteins, which is exactly what they do. These proteins attach to tiny ice crystals that try to form in the cells. They prevent the crystals from growing. They keep them small and harmless. It's like having tiny guards inside each cell, constantly patrolling, making sure ice doesn't take over. These proteins are so effective that scientists are studying them for use in everything, from organ preservation to ice cream manufacturing. The tree also removes water from places where it would be most dangerous. Between cells, not inside them. If ice forms between cells, it's not as damaging. The cell walls can handle some external pressure, but ice inside a cell would be catastrophic. Ice expands. It would tear the cell apart from the inside, rip through membranes, destroy organelles, kill the cell instantly. So the tree pumps water out of cells and into the spaces between them, creating zones where freezing is allowed and zones where it absolutely cannot happen. And then there's the strangest adaptation of all. In the coldest conditions, the water in the tree's cells doesn't freeze into ice. It doesn't even stay completely liquid. It enters a state in between. Scientists call it vitrification. The water becomes glass-like, solid but not crystalline, frozen, but not in the way ice is frozen. It's like the water forgets how to form ice crystals. The molecules slow down so much they can barely move, but they don't organize into that rigid ice structure. They just stop, suspended, neither liquid nor solid. Something else entirely. This glass-like state is incredibly stable. It can protect the cell at temperatures that would normally be lethal. And when warmth returns, the glass gradually becomes liquid again. The molecules speed up, start moving freely, and the cell wakes from its suspended state completely undamaged. It's as if nothing happened, as if the cell was never at risk at all. The tree has turned water into a survival tool. It's broken the normal rules of chemistry. And it does this in billions of cells simultaneously. Every cell protected, every drop of water transformed. The entire tree becomes a fortress against freezing. And all of this happens automatically. The tree doesn't think about it, it just knows. Built into every cell is this ancient wisdom about how to survive the cold. Trees breathe, even in winter, even when they look completely lifeless. The breathing becomes so slow you couldn't measure it without sensitive equipment. But it continues through tiny openings in their bark called lenticels. These are like pores, little breathing holes scattered across the trunk and branches. You've probably seen them without knowing what they were. Small bumps or horizontal lines on the bark. Those are the tree's airways. During the growing season, these lenticels are busy. Oxygen comes in, carbon dioxide goes out. The tree's cells are working hard, growing, building. They need constant fresh air to fuel their metabolism. But in winter, those same cells are barely active. They don't need much oxygen. They're not producing much carbon dioxide. So the gas exchange through the lenticels becomes a whisper, a barely there breath, just enough. Think about your own breathing right now. As you relax into sleep, your breaths become slower, deeper, more regular. Your body doesn't need as much oxygen when you're resting. Your metabolism slows. Your cells aren't working as hard. The tree is doing the same thing. Its metabolism has dropped to maybe 1% of its summer levels, maybe less. So it doesn't need much air, just a trickle, just enough to keep the deepest cells alive. But here's the fascinating part. The tree has to be careful about these breathing holes. If they stay open too wide in winter, moisture escapes. The tree could dry out. Desiccation kills more trees in winter than freezing does. The tree could be full of water, but still die of thirst if that water evaporates through open lenticels. So the tree controls them, seals them partially, covers them with waxy layers, makes them as small as possible, while still allowing that tiny bit of necessary gas exchange. Scientists have measured this winter breathing. They've put sensors on dormant trees and tracked the oxygen and carbon dioxide levels. And what they've found is remarkable. The breathing continues at a steady, incredibly slow rate all winter long. No matter how cold it gets, no matter how much snow covers the branches. Deep inside the wood, cells are still alive, still respiring, still maintaining that thin thread of metabolism that separates life from death. This breathing is proof that the tree isn't truly dead in winter. It's not even fully asleep in the way we think of sleep. Some part of it remains awake, aware, active at the most fundamental level. Life persists, just quietly, just barely, like a candle flame turned down as low as it can go without going out. And this minimal breathing serves another purpose. It prevents the buildup of harmful gases inside the tree. Even dormant cells produce small amounts of waste. Carbon dioxide, other compounds. These need to be released. If they accumulated all winter, they could poison the tree from the inside. So, those lenticels stay slightly open, slightly active, allowing that slow exchange, keeping the tree's internal atmosphere fresh, even when everything else has stopped. The tree breathes, winter after winter, year after year, century after century. That slow, steady breath continues through snowstorms and ice storms and the deepest cold. It's one of the most essential functions the tree maintains. Because breath is life, even the smallest breath, even the slowest one. As long as the tree breathes, it lives. Even sleeping, trees help each other. That underground fungal network we talked about earlier keeps working all winter long. The connections stay active, the partnerships continue, and through those connections, resources flow. Carbon moves from tree to tree through the soil. Sugars stored from last summer's photosynthesis get shared. Strong trees support weaker ones. Old trees help young ones. The forest takes care of itself even when most of it is dormant. Mother trees are especially important in this winter network. These are the oldest, largest trees in the forest. The ones with the deepest roots and the most extensive fungal connections. Scientists have discovered that these mother trees act like hubs, like central stations in the underground network. They're connected to dozens or even hundreds of other trees, and they use those connections to share resources strategically. A mother tree can sense which young trees near her are struggling. Maybe a young tree didn't store enough sugars last summer. Maybe it's in a spot where the soil is poor. Maybe it's been damaged by disease or insects. Whatever the reason, the mother tree knows. Through chemical signals passing through the fungal network, she receives information, and she responds by sending carbon, sending sugars, sending help through the soil. This sharing happens even in the coldest months, even when the forest looks dead. The fungal threads keep working. They don't freeze the way tree cells might. They're protected in the soil, insulated by earth and leaf litter, and they continue transporting nutrients from tree to tree. It's like the forest has a backup life support system that runs all winter, a safety net that catches trees before they fall. And it's not just parent to child. Trees will help neighbors of completely different species. An oak might send resources to a nearby maple. A pine might support a birch. There's no competition down there in winter, no fighting over resources, just cooperation, just sharing. The forest acts like a single organism, a community that survives together or dies together. Scientists have tested this by labeling carbon atoms in one tree and then tracking where those atoms go. They use radioactive tracers that show up on sensors, and what they found is amazing. Within days, those labeled carbon atoms show up in other trees, sometimes trees dozens of feet away. The carbon travels through the fungal network faster than anyone expected. The forest is literally feeding itself through underground connections. This cooperation makes the whole forest stronger. Young trees that receive help from mother trees are more likely to survive their first few winters. They have backup energy, a safety margin, and because they survive, the forest stays diverse, stays healthy, stays resilient. Without this underground sharing, more young trees would die. The forest would have gaps, weak spots, but the network prevents that. It knits the forest together into something unbreakable. So, when you see a forest in winter, remember that beneath the snow, beneath the frozen ground, there's a web of life still pulsing, still working, still connecting tree to tree in bonds of mutual support. The forest sleeps, but it also watches over itself, through fungal threads, through chemical messages, through generosity written into the very structure of survival itself. No tree is truly alone. No tree faces winter in isolation. They're all holding hands underground. This is the strange part about tree sleep. It's active waiting. The tree isn't just shutting down and hoping for the best. It's constantly measuring its environment, testing conditions, asking questions. Is it cold enough yet? Has enough time passed? Are the days getting longer? The tree has to solve a puzzle every winter. When exactly should I wake up? Get it wrong, and you die. Get it right, and you thrive. The stakes couldn't be higher. Wake too early, and a late frost will kill you. Your tender new leaves freeze. Your flowers die. All that stored energy, all those precious sugars, get wasted on growth that doesn't survive. You've gambled and lost. But wake too late, and you miss the best part of spring. Other trees leaf out first. They grab all the sunlight. They get a head start on growth. By the time you wake up, you're already behind, already at a disadvantage for the whole growing season. So the tree has to be perfect, or at least very, very good. And to be good at this timing, the tree needs information. It needs to know what's happening outside. What's the temperature? How long are the days? Has there been enough cold? The tree is processing all of this constantly, running calculations at a chemical level, adjusting its internal state based on what it senses. Different parts of the tree might be at different stages of readiness. The roots might be ready to grow, while the buds are still locked in deep dormancy. Or the buds might be ready while the roots are still sleeping. The tree has to coordinate all of this. Make sure everything wakes up in the right order. Roots first, usually. They need to start absorbing water before the buds open. Otherwise, the new leaves would dry out immediately. They demand water that the roots couldn't supply, and the tree has to account for where it is. A tree on a south-facing slope gets more sunlight. It warms up faster. It might be ready to wake up earlier than a tree on a north-facing slope just a few hundred feet away. The tree on the south slope has to know this, has to factor it into its calculations, has to understand its specific microclimate and respond accordingly. Wind matters too. A tree in a protected valley might stay warmer than a tree on an exposed ridge. Soil type affects how quickly the ground warms in spring. Clay soil stays cold longer than sandy soil. The tree's roots can sense this. They know what kind of soil they're in. They adjust their timing based on that information. Scientists are amazed at how good trees are at this puzzle, how precisely they time their awakening. Year after year, most trees get it right. They wake up at almost exactly the optimal moment. Not too early, not too late, just right. And they do this without a brain, without conscious thought, just chemistry and sensitivity and millions of years of evolution teaching them how to read their environment. The tree is waiting, but it's not passive. It's alert, attentive, processing information constantly, making tiny adjustments to its readiness, preparing to spring into action the moment conditions are right. It's like a runner in starting blocks, muscles tensed, ready to explode forward, just waiting for the starting gun. And that gun is coming. Spring is inevitable. The tree just has to be ready when it arrives. Deep inside the wood, the tree maintains a tiny spark of metabolism, just enough to keep its deepest tissues alive. It's burning stored sugars so slowly you couldn't detect the heat. But it's there, a banked fire waiting to blaze again. This minimal metabolism is essential. Without it, the tree would truly die. Its cells would degrade beyond repair. But with it, life persists, quietly, invisibly, but definitely. Think of it like this. You have a campfire at night. When you're ready to sleep, you don't want the fire blazing. Too hot, too bright, too dangerous. So you bank it. You spread out the coals, cover them with ash, reduce the flames to almost nothing, but you keep it alive. Because in the morning, you'll need that fire again. You'll uncover those coals, add new wood, blow on the embers, and the fire comes back to life much faster than if you had to start from scratch. The tree is doing the same thing. It has reduced its metabolism to the bare minimum, just enough to keep essential processes running, just enough to prevent cell death, just enough to maintain that spark. And this spark is fueled by last summer's sunshine, all those months of photosynthesis, all that energy captured from sunlight and stored as sugar. Now those sugars are being burned, slowly, carefully, making the stored summer last through the dark winter. Scientists can measure this metabolism. They can detect the tiny amount of carbon dioxide the tree produces. They can track how much sugar gets consumed over the winter months. And what they've found is that the tree is incredibly efficient. It wastes almost nothing. Every molecule of sugar gets used carefully. The tree has learned to stretch its resources across months of dormancy, to make summer feed winter in the most efficient way possible. Different parts of the tree maintain different levels of metabolism. The roots might be slightly more active than the trunk. The buds might be more active than the branches. Each part of the tree keeps itself alive in its own way, but all of them are connected. All of them are sharing resources through the wood. If one part runs low on sugars, other parts can send more. The tree balances itself, keeps everything alive, makes sure no part gets abandoned. This inner fire also produces heat, though not much. On the coldest nights, the tree might be a fraction of a degree warmer than the surrounding air. Not enough to feel, not enough to melt snow, but enough to make a difference at the cellular level. That tiny bit of warmth helps prevent ice formation, helps keep chemical reactions moving forward, helps maintain life in conditions that would otherwise be lethal. And here's the beautiful part. This metabolism can be adjusted. If the tree senses extreme danger, it can slow even further, go even quieter, conserve even more. But if conditions improve, if a warm spell arrives, the tree can turn up its metabolism a bit. Take advantage of the better conditions. It's flexible, responsive. The tree is managing its inner fire constantly, keeping it alive but controlled, ready to blaze when spring arrives, but patient through the long winter darkness. Trees have learned thousands of tricks for winter survival. Millions of years of evolution have created countless strategies. Each species has developed its own special methods, its own way of handling the cold. And some of these adaptations are absolutely remarkable. Things that seem almost magical when you understand how they work. Some trees wrap their cells in special proteins. These proteins act like tiny blankets. They surround the important parts of the cell and protect them from damage. When ice tries to form, these proteins get in the way. They prevent ice crystals from touching vital cell structures. It's like bubble wrap for the cell's most precious components. The proteins take the damage so the cell doesn't have to. Other trees pump their cells full of sugar syrup, like we talked about earlier, but some take this to an extreme. They make their sap so concentrated with sugar that it becomes like honey, thick, dense, and this super sweet sap can stay liquid at astonishing temperatures. Some trees can survive with this syrup at temperatures well below zero. The sugar concentration is so high that ice simply can't form. The physics won't allow it. Then there are trees that do something even stranger. They dry themselves out. They pump water out of their cells on purpose. They remove so much moisture that there's barely any water left to freeze. It's like they're mummifying themselves for winter. The cells shrink. They become almost desiccated. But this protects them. Can't freeze water that isn't there. And when spring comes, these cells rehydrate. They plump back up, fill with water again. And it's as if nothing happened. Some trees move sugars and nutrients into their roots for winter. They empty their above-ground parts and pack everything important underground. The soil provides insulation. It stays warmer than the air above. So the roots become a safe deposit box, a protected vault where the tree stores its treasures. The branches and trunk might freeze solid, but the roots stay safe. And in spring, everything gets pumped back up, redistributed. The tree rebuilds itself from the roots up. Bark thickness matters too. Trees in colder climates often have thicker bark, more layers, more insulation. The bark acts like a winter coat. It traps air in its layers, creates dead space between the outside cold and the living wood inside. Some trees have bark that can be several inches thick. That much insulation makes a real difference. It keeps the inner wood warmer, safer, more stable. And then there's the shape of the tree itself. Trees in cold climates often grow differently than trees in warm places. They might be shorter, more compact, with branches that angle downward instead of up. This shape helps them shed snow, prevents branches from breaking under the weight of ice. The tree has sculpted itself over generations to survive winter's weight, winter's burden. Each of these strategies works. Each one has been tested over countless winters. Trees that didn't develop good survival tricks died. Trees that did survived and passed their methods to the next generation. And now we have this incredible diversity of winter survival strategies. This library of techniques, each tree species holding its own secret knowledge about how to dream through winter and wake in spring. Here's something amazing. The tree knows spring is coming before you do. It starts preparing weeks early. Hormones shift. Cells begin to change. The tree is reading signals you can't perceive. Signals in the length of days, the angle of sunlight, the accumulated warmth. It's making predictions about the future based on patterns it has learned over decades or centuries. And it's usually right. The tree measures daylight with incredible precision. Those light-sensing proteins in its bark and buds can detect changes of just a few minutes per day. As winter progresses, the days get longer, not by much at first, just a minute or two. But the tree notices, it's counting, keeping track. And when the days reach a certain length, something triggers inside the tree. A threshold gets crossed. The tree knows spring is coming soon. Temperature patterns matter too. The tree isn't just tracking whether it's warm or cold. It's tracking the trend. Is it getting warmer overall? Are there more warm days than cold ones? Is the soil temperature rising? The tree's roots can sense warmth in the ground before the air warms up. They feel spring coming from below, and they send signals upward. Chemical messages that say, "Get ready, change is coming." The tree also measures accumulated warmth. Scientists call this growing degree days. It's a way of adding up warm temperatures over time. The tree basically keeps a running total. Every day above a certain temperature adds to the count. And when that count reaches a specific number, the tree knows it's time. Different species have different thresholds, but they all use this same basic method. Counting warmth until spring is undeniable. Inside the buds, preparation begins. Remember those cells that have been organized all winter? They start to activate. Genes turn on, proteins get made. The blueprint for a leaf starts becoming a real leaf, cell by cell, layer by layer. This happens invisibly. From the outside, the bud looks the same, but inside, everything is changing. The leaf is being constructed in darkness, in secret, getting ready for its moment. The tree's sap starts to flow more freely. That sluggish winter circulation speeds up, not to summer levels yet, but noticeably faster. The tree is testing its plumbing, making sure everything still works, pushing nutrients up from the roots, getting ready to deliver resources to buds that will soon burst open. You can tap maple trees in late winter and collect this flowing sap. That's where maple syrup comes from. You're harvesting the tree's spring preparation. Bark starts to loosen slightly. The tree is getting ready to grow, to add new layers of wood. The cambium, that thin layer of growing cells just under the bark, begins to wake up. It's been dormant all winter, but now it's preparing to divide, to make new xylem cells for carrying water, new phloem cells for carrying sugar. The tree is planning its spring growth, while winter is still holding on. All of this happens while snow might still cover the ground, while frost might still bite the air at night. The tree is prophesying spring, believing in it, preparing for it, acting on faith that the patterns will hold, that winter will end, that warmth will return, And this faith is built on experience, on memory written in wood, on thousands of successful springs that came before. Winter sleep isn't free. The tree uses precious resources just to survive. Those stored sugars, collected all summer, are burning slowly away. Month after month, week after week, the tree is living off its savings. And by the time spring arrives, those savings will be almost empty. The tree will be running on fumes. It needs to wake up and start making food again quickly. The dream has a deadline. Scientists have measured how much energy trees use during winter. Even in deep dormancy, a tree might burn through 20 or 30% of its stored sugars. That's a huge amount. A massive investment just in staying alive. And if the winter is longer than usual or colder than usual, the tree might use even more. It might drain its reserves dangerously low. Some trees don't make it. They run out of energy before spring arrives. They die in their sleep. Young trees are especially vulnerable. They haven't had as many summers to build up reserves. Their root systems are smaller. They haven't stored as much, so they're gambling on every winter, hoping they have enough to make it through, hoping spring comes before they run out. This is where that underground network becomes crucial. Mother trees sharing resources with young ones, keeping them alive when their own savings run out. Without that help, many young trees would die. The tree also faces other costs during winter. Damage from ice and snow, branches that break under the weight, bark that cracks in extreme cold, roots that get damaged by frost heaving, when the ground freezes and thaws repeatedly, pushing the tree up and down. All of this damage needs to be repaired in spring, and repair takes energy. Energy the tree has to budget for. Energy that comes from those same depleting sugar stores. There's also the opportunity cost. Every day the tree spends. Sleeping is a day it's not growing, not making new leaves, not capturing sunlight, not producing seeds. Winter is lost time from a growth perspective. The tree has to make up for it in the shortened growing season. It has to work harder, grow faster, be more efficient, all to compensate for those months of dormancy. Some trees try to cheat the system. They try to skip winter, to stay active year-round. But in cold climates, this almost always fails. The tree that tries to grow in winter gets killed by frost. Its leaves freeze. Its tender new growth dies. It wastes massive amounts of energy on tissue that doesn't survive. So even though dormancy is expensive, trying to avoid it is usually expensive. The tree that sleeps survives. The tree that tries to stay awake dies. This is why spring is so urgent for trees. When they wake up, they're desperate. They need to start photosynthesizing immediately. They need to make new leaves as fast as possible. Every day without leaves is another day burning through the last of the winter stores. Another day closer to starvation. So the tree pushes out buds rapidly, unfurls leaves as quickly as it can, races to become productive again before the savings account hits zero. Winter sleep is beautiful, but it's also dangerous. And spring is the moment of truth, when the tree finds out if it saved enough to survive its own dream. Some trees have been doing this as for thousands of years. The oldest trees on Earth have experienced thousands of winters, thousands of these slow dreams, each one slightly different, each one teaching something, and together they form a kind of deep knowledge, a wisdom that accumulates over centuries. The tree has learned precisely how to sleep, how to dream, how to survive. There's a bristlecone pine in California named Methuselah. It's over 4,800 years old. Think about that. This tree was already ancient when Rome was founded. When the pyramids were new, it has survived nearly 5,000 winters, 5,000 cycles of dormancy and awakening, and every single time it got the timing right. Every single time it survived. That's not luck. That's mastery. These ancient trees carry knowledge in their wood, patterns, memories, not conscious memories, but biological ones. Information about what works and what doesn't, about which strategies succeed and which fail. Every ring in their wood is a lesson learned. Every winter survived is proof that their methods work. And this knowledge gets passed down, not through teaching, but through genetics, through seeds. The ancient tree's offspring inherit its survival strategies, its precise timing, its efficient dormancy. Scientists study these old trees to understand climate history, but they're also studying survival itself. How does something live this long? How does it survive thousands of winters without making a fatal mistake? And what they're finding is that these trees have incredibly fine-tuned responses to their environment. They don't waste energy. They don't take unnecessary risks. They're conservative, patient. They do exactly what needs to be done and nothing more. An ancient tree doesn't try to grow faster than necessary. It doesn't compete aggressively with neighbors. It doesn't push itself to the limit. Instead, it finds a sustainable pace, a rhythm it can maintain for centuries. It sleeps deeply in winter. It wakes carefully in spring. It grows moderately in summer. And it does this year after year after year with remarkable consistency. This consistency is the secret. Not dramatic success in any one year, but steady, reliable survival across thousands of years. These trees also benefit from stability. Many of them grow in places where conditions don't change much. High mountain slopes, protected valleys, places where the climate is relatively predictable, where winter is always harsh but never catastrophic, where spring always comes eventually. The tree has learned to thrive in these stable conditions. It has optimized itself for this specific place, this specific pattern of seasons. But even ancient trees face new challenges now. Climate change is disrupting the patterns they've relied on for millennia. Winters come later, spring arrives earlier. The timing is shifting, and trees, with their slow generation times, can't adapt quickly. An ancient tree might have survived 5,000 normal winters, but a few abnormal ones might kill it. Scientists worry about this. They're watching these ancient beings to see how they cope, whether their deep knowledge is enough to handle unprecedented change. Still, there's something hopeful in their existence. These trees prove that it's possible to survive, that careful, conservative strategies work over the long term, that patience and precision matter more than speed or aggression. The ancient sleepers show us that dreaming through winter thousands of times is not just possible, but sustainable. That life, approached with wisdom, can persist for millennia. Even now, in the deepest part of winter, the tree is already planning its awakening. Deep in the buds, cells are organizing. The blueprint for spring leaves already exists, tucked away, protected, waiting. The dream is starting to include images of green, of growth. The tree is rehearsing what it will become, preparing for transformation. The awakening has already begun, even though winter still holds the forest in its grip. Inside each bud, there's a miracle waiting to happen. If you could slice a bud open in winter and look at it under a microscope, you'd see tiny, perfectly formed leaves, complete but miniature, all folded up, compressed, like origami. These leaves have been there all winter. They were made last summer, actually, right after the current year's leaves finished growing. The tree was already thinking ahead, already preparing for next spring, while this spring was still fresh. These pre-made leaves are incredibly sophisticated. Every vein is already in place, every cell already formed. The leaf just needs to expand, to unfurl, to grow to full size. It's like a balloon that's already shaped but needs to be inflated. When spring comes, the tree will pump these leaves full of water. The cells will swell, the leaf will open, and within days, what was microscopic becomes full-sized, ready to photosynthesize, ready to feed the tree. The buds themselves are masterpieces of protection. Layer after layer of scales cover those delicate pre-made leaves. Each scale overlaps the next like roof shingles. Water can't get in. Ice can't penetrate. The scales are often coated with resin or wax. Sticky, waterproof. Some buds are so well sealed they can survive being frozen solid. The scales hold everything together. Keep the precious cargo safe through the worst winter can throw at them. But now, as the tree senses spring approaching, changes begin in those buds. Hormones shift. Gibberellins start to increase. These are growth hormones. They signal cells to expand, to divide, to activate. The buds begin to swell, just slightly, not enough to see from outside yet, but internally, the process has started. Cells are waking up. DNA is being read. Proteins are being made. The machinery of growth is warming up. The tree is also preparing its vascular system. Those tubes that carry water and nutrients need to be ready. They've been mostly dormant all winter. Now they need to reactivate. The tree is pushing sap through them, testing them, clearing out any blockages, making sure everything still works. It's like checking the plumbing before you need it, making sure the pipes haven't frozen, that the connections are still good. Root tips are getting ready too. Down in the soil, the very tips of roots have special cells that are always ready to grow. Even in winter, they're poised. And now, as soil temperatures start to rise, these root tips begin to extend. To push forward, to explore, they're searching for water and nutrients, getting ready to supply the explosion of growth that's coming. Roots always wake up before shoots. They need a head start. They need to be functional before the leaves open. and start demanding resources. The tree is counting down now, days until spring, days until awakening. The dream is ending, reality is approaching, and the tree is ready. It has survived another winter, another test, and now it's about to prove it by bursting into life once more. So tonight, as you drift into your own sleep, remember this: you're not alone. Forests across the world are sleeping too. Their dreams are written in wood and measured in seasons. Their rest is as important as yours. And in both of you, sleep isn't emptiness. It's not wasted time. It's preparation, processing, healing, transformation. The tree will wake in spring, renewed, and so will you tomorrow, carrying your own dreams into new growth. Think about what we've discovered together tonight. Trees don't just endure winter, they use it. They transform during those quiet months. They reorganize themselves at the deepest levels. They repair damage. They prepare for growth. They maintain connections with other trees through underground networks. They count cold days and measure sunlight. They remember patterns and make predictions. All of this happens in silence, in stillness, in what looks like death, but is actually a very special kind of life. Your sleep does similar things for you. Your brain is processing while you dream, sorting memories, strengthening important connections, pruning away what you don't need. Your body is repairing itself, healing, rebuilding, getting ready for tomorrow. And just like the tree, you're doing this on a schedule. Your circadian rhythms are counting hours of darkness, measuring light, making sure you wake at the right time, not too early, not too late. Your body has the same ancient wisdom the tree has, the same trust in cycles, the same faith that sleep leads to awakening. There's something beautiful about knowing we share this rhythm with the forest, this need for rest, this transformation that happens in darkness. The tree standing outside your window right now is doing what you're about to do, letting go of the day, entering a different state, trusting that tomorrow will come, that there will be another chance to grow, to reach for the light, to be alive in new ways. And just like the tree maintains that tiny spark of metabolism all winter, some part of you stays aware all night. Your heart keeps beating. Your lungs keep breathing. Your brain keeps monitoring, making sure you're safe, making sure conditions are right. You never completely disconnect from the world. Neither does the tree. Both of you are suspended between waking and not waking, present but transformed, alive but different. The tree teaches us that rest is active, that sleep is necessary, that dormancy isn't weakness but wisdom, that sometimes the best thing you can do is stop trying, stop pushing, let yourself shut down, trust the process, trust that you'll wake when it's time, that you'll know when spring comes, that your own internal clocks and chemical signals will guide you back to waking life. So, rest well tonight, knowing you share this rhythm with the ancient forests, this need for sleep, this trust in awakening. The trees are dreaming their slow dreams of wood and sap and springtime green. You're dreaming your quick dreams of images and stories. But both of you are doing the same essential thing, resting, preparing, transforming in darkness so you can grow in light. If tonight's journey into the secret life of sleeping trees brought you peace, I'd love it if you'd like and subscribe. It helps other wanderers find these quiet science stories. And maybe tomorrow, when you see a winter tree, you'll know what it's really doing. You'll see the dream beneath the bark. Sweet dreams, friend.